All right, so before we get going here, because I know I won't probably get to grading these until at the very easiest later tonight. Where's that? I also had the time set the same for both sections. I meant to have it set to be due before this class started. If you didn't quite finish or you wanted to kind of put some finalizing touches or changes on that midterm extra credit assignment, I'll have the due date set to be, I get this, the end of the day today. All right, so a little bit extra time if you want to kind of go back, review, and make sure that you got everything kind of squared away. Oh, sorry. Squared away with that assignment. The due date should be updated. Just be the end of the day today. Okay. So I will probably, like I said, I might start grading those tonight if I don't see people making second submissions. I'll probably get started on them, but you can submit it again up until the end of the day today, and I'll kind of get your latest submission graded. I'll definitely be able to sit down tomorrow, have a lot more time to kind of sit down and grade those. I don't know if I'll be able to get through all of them. I'm hoping to, but once I do, whether or not that's tomorrow or later this week, I'll kind of get your scores. I'll kind of factor those into your exam scores, get that exam grade updated, and then kind of having that exam score now not just sitting there, but actually kind of carrying weight in your grading class. Right? So you'll see that, like I said, hopefully tomorrow. If not tomorrow, I think I should probably be able to get through it. Excuse me, by the end of the day, Thursday, for sure on Friday, if I haven't got to it then. I've got an exam in my other class, which also kind of brings up that, and I put an announcement up here yesterday. So office hours this week. So tomorrow's office hours, kind of like I did for you guys, I carved them out just for this class and told my other section not to, or courses not to show up. I'm doing the same thing for them. So I'm holding like a more of like a review session for them on Wednesday, so I won't be in my office. I will be around Wednesday morning if you do have a question you want to meet, although there's not a whole lot out there right now. I'm guessing there's not a ton of questions. I also will be available to meet via Zoom pretty much most of the day on Friday. So if you want to schedule a time outside of the normal office hours this week, either Wednesday morning, kind of up until 12 o'clock, or on Friday, just send me an email. We can set that up. Otherwise, make sure you're getting those exam corrections in by the end of the day today. Those should be, I'm not going to call them easy points, but a lot easier points than the other points in the exam. And that'll really kind of help your grade out, since the exam is 32% of your overall grade. Okay. Any questions for me before we kind of keep moving here? So a couple other things I wanted to mention is, after class, when I get back to my office this afternoon, I'll put up the next quiz. So I gave you the practice problems last week. So they're kind of sitting up there. It's going to be about nonlinear relationships, which we'll finish up talking about today. We might revisit them at the very beginning of next class, just to kind of set us up for the next topic. But we'll have covered everything that you would need after today to kind of take that quiz if you wanted. So I'm going to get that posted up. It'll be due by the time we start class next Thursday, right? So you kind of have about a week and a half to do that. I'll post up the next problem set, which will be due at the end of the week next Friday, right? So I'll revisit this in Thursday's class as well, but you'll see that next quiz and next problem set pop up. It'll really just be related to this idea, this topic of nonlinear relationships, which we're going to start covering topics that cover not just like, before it was like weekly, we were kind of updating what we were doing. Here, they're probably going to be like a week and a half, so like 3 class periods. By the time we get to the end of the semester, there'll be some stuff that like it's a broad category, so we might actually take like 2 weeks to do it, 4 class periods. So for this last week, and then for today's class, we'll have nonlinear relationships. Next class, and then next week, we'll talk about interaction terms. Okay. So I put all the files up there because we're going to be using them next class, but today we're still going to just be using those nonlinear relationship files. Okay. I also updated the do file just to kind of include some stuff that we talked about last week that wasn't in the do file, and then also some stuff that I'm going to add in today that wasn't originally there. Okay. Let me think. Other than that, I don't think I have anything kind of housekeeping wise. Any questions for me before we jump into material? Okay. Also, since you guys are all here prompt, I'll give you maybe a little bit of added bonus for that. We'll also go back to using in-class quizzes. I very may well have an in-class quiz on Thursday's class. High likelihood, given that I'm running the class. Okay. So where did we leave off? we were talking about logarithmic specifications. And just to kind of summarize what we had talked about in terms of estimating these relationships that are nonlinear. So I'll try to use terminology that lines up with the slide. So we had these linear log models are the first ones that we had. So the way that we write these, it's always going to be the order in which we would estimate this regression. So the first word is going to be my dependent variable. Anytime I was taking the natural log of something, right, that second term, that's my independent or my x variable. So if we had a model that looked like this would be our linear log model. Okay. This was going to allow us to estimate not just a linear line of best fit, but something that has some curvature to it. Okay. We said, how do we interpret this coefficient from a linear log model? I'll also accidentally sometimes call this a level log, level, linear, those kind of terms are interchangeable. We're just talking about using the units. So now it's not a 1 unit change in x. By taking the natural log, what did I converted kind of x into? We said percentage changes. So it's now a 1% change in x is going to be causing our predicted y value to change by what? Not just the coefficient now. If we're going from percentages to just units, so we can kind of think about this as going from percentages to probabilities. So how would you convert a percentage into probability? You would divide, I hope you guys know this by the time you're in your college career, right? You would divide by 100, right? So predicted y to change by whatever this is, units, right? Because y is still in units. Y is still kind of this linear, this level kind of model. Okay? We said we also had a log linear relationship. Once again, we write it the same way we write out the regression equation. So the first word is my y variable, second is my x. So here, the log of natural y is going to be some function, just of x, right? X is in linear terms here. So how would I interpret the slope coefficient now? Well, now it's a 1 unit change in x because x is just in levels, or it's the linear term. And it's going to be causing the predicted y value to change by not just beta 1, but if I'm going from a level or units to a percentage, I need to multiply by 100. And now it's not a unit change in y, it's a percentage change. So this was kind of our general interpretation of these level linear log linear models, right? And we talked about one at the very end of class as well. We'll kind of revisit that one here in just a second. Okay. Big questions on this. It's looking hopefully familiar with what we had at the end of last class. So we were using this college GPA data set. So before we kind of talk about model comparison, we can think about why might I want to do this? Well, it's because we had different percentage changes, right? That sometimes, so for example, if I'm thinking about the amount being saved, and then I want to think about income, going from $40,000 to $50,000, I may not save a whole lot more, right? Even though that was a relatively large percentage change of my income, I might go from 250 to 260,000. That might be a small percent change, but when I make $250,000, I have a lot more disposable income. I might invest all of that additional 10,000. So it's going to be the effect is not going to just depend on the units, but what that percentage change is in that x variable. So what we can do to determine is the linear log model better than our linear model. That was our just typical normal average models we've looked at up to this point. Well, one thing I can compare is my r squared, right? Just using that natural log term, explain more of the variation in my y variable. What I can also do is look at the statistical significance. So I can run the linear model and the linear log model and see okay, does the linear term of X have more statistical significance than when I use the natural log? Right, both of those two things would be indicators of which model I should use. So we'll take a look at an example here, which we left off with last class. So just kind of to revisit where we were at. And it's that GPA data, which I still forgot to move to this class. So I've got it in my 371 files though, because I know I like to use it. So we're going to scroll down. We were right here. All right. So I'm going to create this new variable, which is the natural log of high school rank. I'm then going to kind of run my linear regression, my linear regression, and then my linear log model, right? For the relationship between college GPA and high school rank. So I'm going to run both of these. So what model is a better fit? Well, we can compare two things. So from my level model, or my linear model, this term of level or linear is interchangeable. I just teaching different classes, I use the term differently and I continuously go back. So I will try to keep using linear, but I might slip into saying level occasionally. So this linear log model, the linear model explained 0.1125 proportion of the variation in college GPAs, whereas my level log model explained 0.16. So the R squared was significantly higher from my level log model, so that would be one indicator that that's the model I should be using for that, to capture that relationship between college GPA and high school rankings. Okay, that percentage changes in high school rating might matter more. Now, I could also look at, well, what was the statistical significance of the linear high school ranking versus the logarithmic term or the nonlinear term? Well, there I have a p-value in both scenarios of 0. So which of these was more statistically significant? So even if I can't tell from the output of the p-value, which of these was more statistically significant? The level or the linear term of high school ranking? Sorry, the linear or the logarithmic term of high school ranking? So the linear, so it has a smaller test statistic, right? So if I have a smaller test statistic, what's that going to look like? If I can get this there. So whether or not we're using T statistics, F statistics are a little bit easier, but even if we're using T statistics here, if I found, and I think they were negative, but just for the sake of this example, let's say one was 22. So I believe this was the test statistic from the linear term. The other one was something like 28. This was from my nonlinear or that logarithmic term. What's going to be true about the p-value then from the model that had a higher coefficient or a higher test statistic associated with the coefficient? The p-value is actually going to be lower. So if the p-value is lower from this model, is it more or less statistically significant? More. So what model would I prefer? A model that has more statistical significance. So in this case, it ends up being the exact same model that the R squared also predicted was better, right? And quite often, those two things will line up. We'll have occasional examples where they don't, but for the most part, those are the two things that are going to be strong indicators that we should be using this linear log model instead. Okay. Any questions on that before we keep moving? This I think we talked some of this last week, but I'm kind of revisiting and reviewing a little bit. So, what if instead we were also concerned with this SAT score's relationship with college GPA? So I'm going to create the natural log of this SAT score variable, and I'm going to run this regression just so we can get like another example. So here I've got my linear and my linear log model. So which of those would best fit the relationship between the linear term and the logarithmic term? So which one has a higher R squared? I'm looking at this model. I have the linear term of SAT. Here I've got the nonlinear term. Which one has a higher R squared? The linear. So for the relationship between GPAs and SAT scores, it actually looks like, oh, the linear model better captures that relationship, right? Now, what about the statistical significance of the coefficients? Well, in the linear model, this was 28.8. Nonlinear model, 27.9. A little bit closer there, right? It's not quite as big a gap, but the higher test statistic would still have smaller p-value. So both indicators here suggest that for SAT scores, we should be instead using that linear model. Okay. So this is kind of our first look at like what we would call model selection, right? Which one of these better fits that relationship? Okay. Questions on that before we keep moving? All right. So the next thing that we'll talk about, oh, that's not the tab I wanted, is comparing models where we're looking at maybe joint significance. So maybe I could do joint significance tests with these linear, nonlinear relationships as well. So maybe I've got one model where I'm only including the linear terms, one where I'm only including the nonlinear terms. Now, not for one variable, for both high school ranking and SAT scores. What I could do is run the full model where I've got both the linear and the nonlinear terms, and then run basically a joint significant test, calculate our F statistics, and determine, can I say that the linear terms have joint significance? If I can't, if I fail to reject that, that would mean that that model isn't very good, that the linear model isn't doing a good job of capturing the relationship between these variables. If I run that same test, but for the nonlinear terms, well, there, if I could reject it, remember, these joint significant tests, we're assuming the coefficients are 0. So if I can reject that, what I would be saying is, oh, the nonlinear terms actually are statistically significant with my y variable. They do a better job of capturing that relationship. So I can test for the joint significance of these kind of nonlinear terms. Now, this isn't always going to lead us to a clear answer. So we'll kind of see why. So I tried to find an example where this was the case. And I think I've got one later on where it looks a little bit easier. But let's say I run this full model. All right, I've got the linear terms and the nonlinear terms of SAT and high school ranking and their impact on college GPAs. So I'm just going to run that full model. This would be my unrestricted model. It includes all of these terms. Right? Now, I don't see it behind the scenes, right? But what I could do is think about if I want to test the linear terms here to see are they jointly significant, what would my unrestricted model be? Whoops. Or sorry, what would my restricted model be? Well, if these are my restrictions, the restricted model is when those are left out. So my restricted model would actually be, or my comparison is when I only have the nonlinear terms. Now, when I run this test, that regression gets ran behind the scenes, but it never shows it to me. I'm just going to run it so we can kind of see it to compare. So, for example, if I run it only with the nonlinear terms, and then I run it with every single, the linear and the nonlinear terms, it goes back to what we were doing before. We now have the restricted models R squared. If I add in additional variables, what do I know has to happen to my R squared? It has to go up, right? So what do I need to do? Well, I know my unrestricted model will have a higher R squared. Sure enough, 0.26 instead of 0.25. But when we're doing this test, it's almost like we're saying when we added in these additional variables, right? Were they explaining more of the variation per variable that we had? Now, it's not exactly what the F test is doing. That's one way to kind of help think about it, right? So it'll run these behind the scenes. We could take our F test calculator. We needed the R squared from the restricted, R squared from the unrestricted, sample size, number of restrictions, number of variables in the unrestricted model. We can compute this ourselves, or we can rely on Stat to do this for us by just using that test command. It'll do all that work behind the scenes and then just spit out at us that F statistic. So I'm going to run this. So when I'm doing a test for those nonlinear terms, I end up with a p-value of basically 0. So this joint significance, we start out assuming that both of the coefficients on the linear terms are equal to 0. Can we reject that? I mean, with a p-value of 0, you can reject everything, right? So yeah, we can reject that they're equal to 0, or basically we're saying those linear terms have some statistical significance with our y variable of college GPAs. So this would suggest that this is a good model. The linear terms are actually capturing that relationship. Now here's where it can get kind of weird. If I then run a test where I'm looking, okay, what if I run the restrictions that I have are not the linear terms, but the logarithmic terms, these nonlinear terms. Well, there, I still assume that those, for a joint significance test, that those two coefficients are equal to 0. But now, can I reject this joint significance? That there is no joint significance, right? Well, I have a p-value of 0, so yes. So that would suggest that the nonlinear terms are actually capturing the relationship. So now I have a problem, right? Because both tests, I rejected the null, which would mean both would suggest that both of these were good models at capturing that relationship, right? Do you have a question?
Well, what is the difference between linear and non-linear terms? Because everything seems the same.
What do you mean?
Like, if you see the results are the same.
These results?
Yeah.
Yeah, so we have high p-values, right? So it looks like they're the same, but are they? What's the F statistic?
Oh,
Different, right? So this is, again, a scenario where if we just look at the p-value, it looks like both of these we can reject at any level, and that's true. But one of them has more statistical significance. So we can end up with a scenario where I rejected both joint significance tests, which would mean both of them suggested that the linear model was good and the nonlinear model was good. So now what do? Well, now kind of what's the tiebreaker? If I had this scenario, I'm going to have to look at which one has higher statistical significance. Which of these can I reject with a higher level of statistical significance? The linear model or the nonlinear? With a test statistic of 73, what's true about my p-value compared to when it's 22? It's a lot smaller. So this would be the model that I would kind of choose, right? Yes, I can reject both of them, the linear and nonlinear kind of assumption that they're equal to 0. But this one I can reject it with a higher level of statistical significance. We'll have an example later on in class where sometimes it's a lot easier for us, where we only reject one and we fail to reject the other. But this can arise where you actually end up rejecting both the linear kind of restrictions and the nonlinear ones, and there kind of our tiebreaker would be which one has more statistical significance.
okay. So since F has greater value, we are rejecting the linear one.
So remember, we're starting out assuming that they have no effect. Rejecting that means we're saying there is an effect. So in both cases, we said there is an effect from the linear terms and there is an effect from the nonlinear. But which of them have a higher statistically significant effect? The one with the higher test statistic. Yeah. All right. So let me think. Is there anything I want to say here? We kind of talked about this, if I remember right, at the end of last class. First of all, were there any other questions on that? I can kind of go back and revisit it, but yeah.
What does that say about the true relationship? If they're both statistically significant.
So when we're doing that, what we're trying to make a determination between is if the linear or the logarithmic terms are better. So what might, if both of them look like they're significant, maybe it's that there's some other equation that would capture that relationship even better. That's the short answer of it. And this is just like our first glance at thinking about testing these models. So in theory, we would probably want to investigate maybe cubic relationships, maybe, right, some of the other stuff we talked about last week. Or maybe it could be that the function isn't as simple as a logarithmic. It could be some crazy, like in fact, this is probably bore some of you, but like when you get further into economics, you do what we call structural estimations, where you kind of know like what the production function is, and you know that it might be the natural log over the squared term multiplied by to the negative, like you kind of know ahead of time what that equation looks like. And so you would estimate the relationship to be that function. Here, we started out just with linear. We're just slowly progressing into like easier nonlinear functions. So I think you can make them like, yeah, those structural estimations that they do, or you're estimating like a crazy production function that has like not just a natural log, it's really complicated. Yeah. Is that, well, I know that's not like the best answer, but yeah.
Yeah, thanks.
So one thing that we talked about also last class is we can also look at, and I did this right at the end, so it might kind of forget, log models. So this is where we are taking the natural log of both the independent and dependent variables. So we said now, what's the interpretation of beta 1? it's a one, not unit change, but a 1% change in X because we take the natural log of X. And it's going to be causing the predicted Y value, or predicted Y, to change by what? Beta 1. But if we're going from percent to a percent, we don't need to scale it. So now the interpretation is just that it's going to change Y by beta 1. Well, Y is not in units, Y is in terms of percentages. All right. So we said, what does this start to look like? Remember we said at the very end of last class.
Elasticity.
Yeah, what if this was quantity demanded? What if this was price data? I could estimate price elasticities, right? Or income elasticities, or cross price elasticities if I had a data set. Okay. Any questions on that? Okay, so I think what I want to do here, we're going to start using that happy data set. Is there anything else I wanted to say before we move on? Yes, okay. So we kind of have already jumped the gun and talked about this, but we already talked about we can do log linear models. We can also do log models. Now, just to revisit one thing we talked about last class, when I have these models where I'm taking the natural log of my dependent variable, what can I no longer use as my dependent variable? I can't take the natural log of 0, so I can no longer use dummy variables, right? I have a lot of zeros in there for a dummy variable, right? Or some categorical variables will have zeros. It also becomes problematic. Let's say I wanted to use the Y value of income. What could happen? Someone could have an income of, you drive by Seminary Park here in Bloomington, 0, right? So what's that going to do? Well, I can't take the natural log of 0. It's going to throw out all those observations. That's going to cause a problem for us, which I think we'll see here in just a second why. Okay. So we can't use these dependent variables that have zeros in them. Now, what can we do? We already looked at this. We're going to start to compare our specifications. So at this point, we talked last week about quadratic models where we included a square term, cubic models, really any polynomial that we wanted to look at, we could do. We now have these linear, log, log models. Which one best fits the relationship between this X and Y variable? That's what we want to determine. Okay? Well, we have some limitations, right? We can use those polynomial specifications where we either include a square term or even cubic terms, right? And we can compare those to our linear, and our linear log models simply by using the adjusted R squared. Now I'll talk about why up to this point I've kind of just been using the R squared. I'll talk about why we can't use it to compare across these three. So maybe to make this a little bit easier, this slide a little more digestible. I think this is a good summary, right? So if I've got models we talked about last class, where I could include a square term, right? I can compare those to my linear log models, right? I could also compare these to just my typical linear models, right? Now, the reason why is because all of them, my R squared is going to tell me what? It's the proportion of the variation in my Y variable I can explain. All of them have the same Y variable, right? The same Y values. So I can compare the R squared. Earlier, we were looking at the difference between our linear model and our linear log. In fact, I was actually here, I'll call this like our polynomial models, right? Excuse me. I could just compare the R squared here because I had the same number of variables, right? When I want to start to compare these to my polynomial models where I had square terms or quadratic terms, by adding in these square terms, it's essentially like I'm adding in additional variables. So what will always happen to the R squared? It goes up. So what do I need in order to compare to these squared or these cubic models? That's where we need to use. And here I was kind of writing adjusted R squared. sometimes just to make it easier, I'll just write it like that, right? We can't actually use the R squared to compare to those old quadratic or those cubic models because I'm adding in more terms. I know the R squared is gonna be higher. There, what am I gonna do? I can compare the adjusted R squareds. All right, so just one kind of additional step, nothing crazy there. Now, if I'm thinking about instead my log linear model, so this is where I took the natural log of y, but I was just using the linear term of x. Why can I not compare that model to these other three using the R squared? It's a different y value. When I take the natural log, inherently that distorts the variation that exists in y, right? So it is a function that does not equally change every single value the same, and so my variance is going to change. So I cannot, simply using the R squared, compare those two models. Okay? Now, what models can I compare? Well, what other model would have the same y variable? I can compare my log model, right? Because there I have the same y value. So I have the same variation in that dependent variable. Okay? Good questions on that.
Can you explain the last part more?
Why I can compare these two? Because here I'm changing my independent variable, but my dependent variable is the same, right? So the variation that exists in the natural log of y will be the same between these two regressions. It won't be the same as the variation that exists in the actual y. So in fact, so if I go here, so let's say my y variable I was using was what, college GPAs, and then did I call it natural log? Did I create this variable? No. So let me see, right here. So to make this point, I'm going to run this code right here. So here I took the natural log of college GPA. Notice for the natural log of college GPA, for my log level and my log model, once again, it goes back to I can simply compare R squareds. I could compare the adjusted R squareds. Here, both of them suggest that the log level model is just slightly better, right? Once again, with these simple models, I can also just compare the test statistic. The test statistic's a little bit higher. So it suggests that that log linear model is a little better than the log model. That's because in both of these regressions, I have the same y variable. If I were to look at, well, we can use the standard deviation as our measure of variance. So then I'll do, when I look at the variation that would exist in my y variable, the standard deviation is 0.65. If I look at the natural log of that y variable, what's the standard deviation now? Only 0.29. By taking the natural log, I'm changing the underlying variation of that y variable, so I can't compare regressions where the dependent variable is the natural log to where it's just that linear term. Yep. And everybody, let me get everything down here. Any questions before we keep moving? All right. Also, you can do what you want, whatever works good for you. I might be saying this because I'm jealous that I didn't really have the same capabilities when I was in college. I couldn't have taken a picture unless I was like 5 feet away from it with the phone that I had. But it's great to take pictures of this stuff. I will say there is I'm not a physical science. I'm not like a biologist kind of, but I do know there's some evidence that writing things down, just like the kind of muscle movement, can help you remember things more. So it's great to take pictures, but taking notes still has some value in it. Once again, I'm also probably just saying this because I'm jealous that I couldn't do this. So let's go back and think about, I want to go to the slides. There we go. So just to kind of round out this discussion, we can compare some of these models, but we can't compare others. So at the end of the day, sometimes we'll run into in practice, we'll run into this situation where I have to just make some judgment call, right? Like I have to think about what the two variables are and whether or not, what that relationship would look like and which one of my models kind of would best fit that scatter plot, right? A log level, level log. We won't dive into like how you would, how we make those determinations. We're going to use all the statistical tools we have available to us and try to use those to make our best model selection, right? But there will be some scenarios where you get down to it, and I can't compare the log level to the level log model, right? Or at least there's no perfect way to do it up from what we've talked about up to this point, okay? But I won't ask you to make those comparisons, but just to kind of be complete in our discussion of this. So the next thing that we're going to move on to is revisiting basically what we talked about last class, combining what we talked about today, using a different data set. So we're going to live in Stata for most of the rest of the class. So I'm going to open up my happiness data file. I don't really care about this data, I can lose it. And I'm going to run this very simple regression. It didn't have a lot of variables in this data set. Had this weird happiness measure, and we'll look at it here in a second. It was only like 3 values, so it was kind of a weird variable. But we're just going to use it because it measured self-reported happiness, right? So think about higher values, so that meant someone felt happier in their life. I then included the variables of hours worked on average each week, the number of children, the age of the individual, right? So interpretations, working 1 more hour on average each week makes me happier. Why? So I'm not controlling for income here, so probably I have more money, right? Having another child makes me happier. Well, I'm glad this isn't negative, right? 1 year older, this one kind of goes against what I would have thought. I would have thought being older makes me a crotchety old man, but apparently here, getting older, maybe you recognize, you take more solace in the small things in life, and then even the small things bring you more happiness the older you get, right? I was thinking about this walking over here today. I mean, you guys probably, maybe you don't take it for granted. I've been at other institutions, and as a Purdue grad, this pains me, but this campus is absolutely gorgeous today. You walk around a day like today, I'm just like, how can you not just like stop and take it in, right? So maybe that's me getting older, right? I don't know. But so we have these linear models, right? I can, so all the stuff we're doing up to this point, I wasn't adding in any additional controls, but we can, right? So I'm going to want to investigate this relationship of hours worked with happiness, but I can still do that, including additional controls. We're not limited to just, only having one X variable, right? So the next thing I wanted to do was think about, okay, I think that maybe, I don't want to go into the linear log stuff yet. I just want to look at, would the squared term make sense? Right? Now I've got children and hours squared here. I don't think we'll have time to investigate this children one. I might start out with this next class. But we'll run both of this line of code. All I'm going to do here is create a variable that is the squared term of these variables. So children times children is children squared. Hours worked times hour worked gives me hours. Probably could have put hours worked squared, but I put hours squared. Right? Now, you don't have to do this. In fact, I'll come down later and mention, we had that shortcut where you could use that CDOT command. But I think maybe after we work through this example, you'll see why even I prefer to use this method. I said in practice, if data sets are large, you're adding in more variables, sometimes computing space becomes an issue. For the most part, computers are insane now, so that really isn't as much of an issue here. I like to do this because I now know what the variables are called, right? So I've now got my hours squared, which represents my hours worked squared, okay? So I'm now going to rerun that regression, but not just include the linear term, I'm going to include the squared term as well, okay? So run my regression. If I were to compare these two, the model where I include hours squared, what do I know is going to be true about its R squared relative to when I only include the linear term? Well, I've included essentially an additional variable. So what should happen to my R squared? It should be high. What should I instead be using? My adjusted R squared. It accounts for that. So if I compare my adjusted R squared, 0.0017, we're not explaining a lot about the variation happiness, so we should take these results with a grain of salt. The adjusted R squared a little bit higher from that model where I include a square term. Now you'll notice in this case, if I would have used R squared, I would have been okay. I would have made the right decision. But that gap, notice, from our squared term, so we have like what? 0.002. up here, it was 0.01, so that gap is different. So it could be in some scenarios, when we use the adjusted R squared, we might make a different decision than simply looking at the R squared. Okay, so you want to make sure when we're looking at these squared models or these cubic models, you're comparing adjusted R squareds. Okay? So it looks like this squared term actually explains more of the variation in our y variable of happiness. Now, what's a second indicator? What's the statistical significance on that square term? Well, it's statistically significant at what levels? P-value is 0.02. 5%, right? It's less than 0.05, and it's also less than 0.1, so the 10.5% significance level, which corresponded, we can say that that squared term has a statistically significant effect with happiness at the 90 and 95% confidence level. Okay? So both indicators that we should be using that squared term to better fit that relationship between happiness and hours worked. Okay? Now, when we're talking about these squared models, and just to revisit this, because I don't think we looked at this in Stata. If I had kind of happiness here, now I'm thinking about it was a function of hours worked, but we also included a squared term. Right? Well, we're thinking about the marginal effect. So the marginal means change. So if you guys had intermediate micro yet? So you're taking a lot of, I don't know, maybe they don't have you do this, push it as far, but derivatives, right? Change in happiness from a change in hours worked. We're essentially taking a derivative to get our marginal effect. So what would the marginal effect be here? Take a derivative in respect to this thing that's changing hours worked. 2 times beta 2. So you can see the marginal effect here depends on the value or where we started out at for hours worked. Right? So if I wanted to say the marginal effect of working 1 more hour, I would plug in whatever hours worked I saw. Let's say I go from 40 to 41. I would think about starting out at hours worked of 40. What would the marginal effect of 1 more hour worked be? I can get these coefficients from Stata. Now it's just a little bit of math. All right. So if I were to estimate this relationship, and we had the results up there already, but as you start to work more, initially going from like 20 hours, 21 hours, you're making more income. That probably brings you a pretty good level of happiness. You can, affording more. At a certain point, if I'm working 80 hours a week, what's the marginal effect on my happiness of working 81st? It may become less or negative at some point, right? So my intuition would be that the linear term is positive, the squared term is negative. Sure enough, if we look at the regression output, we have a positive coefficient on the linear term, negative on the squared term. Right? So if you wanted to find the marginal effect, you could just simply use these two values. This is your beta 1, this is your beta 2, and you would plug them into this equation. Right? And then you could make predictions for what the marginal effect was at 40 hours a week, at 60 hours a week. You could do this all by hand. So I'm going to show you what I think is a nice way of doing it in Stata that's a little bit easier than doing it by hand. Now I won't expect you to do this. If I ask you on this next problem set to calculate a marginal effect, you can do it by hand, right? As long as you obtain those coefficients from Stata. You have to do that part in Stata. You can still make your predictions by hand, but I think this is like a better way of doing it and might help. I don't know, if you're trying to, once you get to a job, they're going to want you to do as little amount as possible by hand and as many things as possible using some type of computer software, right? So how could I do this, right? So I'm going to run this regression where I have this squared term. What Stata does, it stores up all these coefficients that it shows us. It's storing them behind the scenes. So I can use those coefficients. So the way that you do that, and I just use this display command, that's just going to tell me what this function equates to. So here was my marginal effect. It was the coefficient on my linear term, so the coefficient on hours worked here, plus 2 times the coefficient on my square term, that was beta 2, and then multiplied by whatever value of x I'm trying to make the prediction for, right? Whatever I'm trying to calculate the marginal effect for. Okay? So here I said, let's just start out at a 40-hour work week. What would the marginal effect of working one more hour be for someone? So the syntax is always underscore B that says take the coefficient of what? Whatever variable I'm putting in those square brackets. So if I run this, it tells me the marginal effect for working one more hour on my predicted happiness is 0.002, starting from that hour's worth of 40 hours. Now, we said that because this coefficient on hours squared is negative, if I were to make my predictions instead for what's the marginal effect of one more hour worked if I'm already working 60 hours a week? Well, if that coefficient on the squared term is negative, multiplying it by a larger number, this is a larger negative value. What's happening to my marginal effect? Going down. So if I run this, I should hopefully, if I'm not lying to you, see a marginal effect that's smaller. All right, it's getting closer to zero. Okay. Any questions on this before we keep moving? So one other additional thing we can do using this marginal effect is if it's decreasing, there will be an hour's worked where it eventually becomes negative. Why might you want to do something like this to find like where that turning point is? I teach intro micro, so right, like hopefully you guys remember this. What's happening if your marginal costs are decreasing when you're increasing output? You've got gains from specialization, right? This is the idea of like my marginal productive worker, right? Gains from specialization, so my marginal costs are decreasing. There will be a turning point, right, where they'll start to increase. Now, here I'm thinking about marginal costs. It's not negative, positive, but we're interested in turning points essentially, right? That's what I'm trying to get at. So, how would I find where the marginal effect goes from positive to negative? Well, that would be when it was equal to. So I'm just going to set this equal to 0. Rearrange things a little bit, and I would end up with so this will always be kind of the form of our turning point for calculating when that marginal effect is 0. It's going to be negative, whatever the linear terms coefficient is, over 2 times the nonlinear terms. Now here, remember, we had a negative value here, so once we plug a negative in here, that's going to cancel. But we can do this and state it as well, right? We can use those coefficients. So what's that going to look like? I'm just going to take that coefficient on hours worked. I actually forgot here my negative sign. Right? I'm going to divide that by 2 times the coefficient on the squared term. And this should tell me where that turning point becomes 0. Now, I had the predictions for 40 and 60. So where should that turning point be above? If it's still positive, it must be somewhere above 60, right? Sure enough, if I run this, I find that it's 73, right? So it tells me once I get to 73 hours a week working one more additional hour, yeah, I'm making more money, but you know, I want to go drink a beer at the local watering hole, right? And so it's having a negative impact on my happiness, right? So we can kind of find these turning points by using those saved coefficients as well. Once again, you can grab those coefficients. You could write down these numbers, plug them into that and do it by hand. But this is one way if you're just kind of interested in coding and you're starting to think about how you can maybe push yourself a little bit, you can do all of this and state it as well. And I've noticed a couple of you have used like this idea. You must have Googled it or used stayed in some other class. You can use these stored coefficients. Okay. So the second half of the class, I sometimes will drop things in that I don't necessarily expect on the problem, but you know, kind of push into that next level. Okay. Any questions on that before I keep moving here?
Can you show the phone line again?
Yes.
Thank you.
All right. So. Oh, what do I want to do next? We got happiness. Oh, I'll show you that and then we'll talk about logarithmic stuff. So we're looking at 25 minutes, we should be fine. All right. Now, I'm gonna gloss over this. And you can do it this way. I just see more people make mistakes, and honestly, it confuses the hell out of me when I do it this way. And I sometimes have to, but I don't like it. If you don't create these variables and you use that CDOT command where you use the double hashtag. So if I run this regression, it gives me the exact same results as I had up here, right? When I created and included the squared term, that's what it's doing. The only problem is, what's the variable name now for my squared term? It's this, right? I mean, I can see that that's hours worked time. Okay, that's the hours worked squared variable. But then I gotta like type that out. And yeah, there's generative AI, but sometimes it's easier for me just to create the variable and kind of have a short word to have to type in there. So that's, you can do all of it that way. And notice I can still use that stored coefficient on the square term. It's just I got to type all that in now, or I got to use that, and it's just not as clear. So for me, I actually know that I'm a very inefficient coder because I like to use long variable names. I like to use things that really help me to know what I'm looking at. So an efficient coder would tell you to do this. I'm not an efficient coder. I want you to get though to understand better what you are coding. So I would probably suggest creating your own variable. You can name it what you want so that you remember what it represents. Okay. Any questions on that? I know I'm glossing over a little bit. I don't, if you want to use this method, you can, if it makes more sense to you. I just think I don't know, takes more time and it becomes a little more confusing. So the next thing we're going to do is start to compare these different models to the quadratic model or squared term model, which is our different log kind of linear combinations. So right off the bat, I'm just going to create the natural log of hours worked, happiness, and age. Okay. So I've now got my natural log variables. Now notice I've got to be careful, and I'm still going to make these acting as though this didn't happen. But missing values, okay, the age one shouldn't matter because it should have just been kicking out missing variables there. I shouldn't have anyone with an age of 0. Happiness, none of those should have been 0. I could have an issue with this hours worked. When I'm taking the natural log, we said we can't take the natural log of 0. So it could be that people had in 0 hours worked, and it's now getting rid of them from my data set. That's not a good thing, right? Because when I compare these models, say I want to compare the level log to the level, or linear log to the linear, I want it to be the same set of observations, right? So I have to be concerned if it's kind of dropping observations because there's 0 value. So here, I know there's no zeros, but this was just missing values, so it can't use those observations in any of my regression. I also know for age, you weren't in this data set if you had an age of 0, so that was just missing values. These ones I might be concerned because if you actually look into it, I'm pretty sure. So if I do some hours worked, okay, my concerns are alleviated because even the lowest possible one was 1. Those must have just been missing values as well. If I'd seen a minimum of 0 here, well, now it's kicking out observations when I'm taking the natural log and those specifications, and I'm comparing different regressions that have different number of observations or different samples. I don't want to do that. So I want to be really careful with variables that I think might have zeros in them if I'm trying to compare across models. I must have had it. I probably chose this for a reason when there was no zeros in here. So we're then going to come down here. So this is going to be similar to what we did before, where I'm going to run some joint significance, where I think about maybe hours worked and age. I want to know whether or not they have a jointly significant relationship with happiness, the linear terms, and then the nonlinear terms. So I've got hours worked, age, but then also the natural log of both of those. So I run this regression. This would be my unrestricted model. Now, if I ran the restrictions where I was leaving out those nonlinear terms, right? So I'm saying basically this F statistic that I'll get, it's telling me, including those nonlinear terms, can I reject that they have 0 effect? If I can reject that, that's telling me I found evidence that they have an effect on that Y variable. So I run this regression, I get a p-value of 0.47. So can I reject that the coefficients on those nonlinear terms are equal to 0? At a p-value of 0.4, Not any of our conventional levels, not even close. So this would be evidence if I can't reject this, what does that tell me about the nonlinear variables? Their effect is, if I fail to reject this, their effect is jointly 0. So, is the nonlinear model a good one? No, right? It looks like the nonlinear terms have 0 impact on that y variable. Now, hopefully, when I run my test for whether or not the linear terms have some joint significance, hopefully I see there that they do. Sure enough, okay, it's not at our highest level, but when I run this joint significant test for the linear terms, at the 10 and 5% level, I can reject this null. Well, if I'm rejecting that they had no effect, what I'm really saying is I found evidence that they did have an effect. So it looks here like the linear model better captures that joint relationship between hours and age and this level of happiness. Okay. So before we had an example early on where like they were both, we could reject both and we had to choose one that had a higher test statistic. Well, here, once again, we're still choosing the one with a higher test statistic. It's just now it's very clear that that linear relationship is the one that is better than the nonlinear relationship. However, that was when we were looking at joint significance. Okay. So we can do kind of a similar thing, but now I'm like, okay, maybe it's that hours worked and age don't both have a nonlinear relationship. Maybe it's only one of them, right? So I'm going to look at just this hours worked variable because I had evidence earlier from the square term model, the quadratic model. We said that that actually looked like it was better. So we have some evidence there is some nonlinearities in this relationship between happiness and hours worked. So I'm going to run this regression, just the linear model, and then run one where I have the linear log model. Okay. So I'm going to do that. And compare the two. So what happened to my r squared, or even if we wanted to use the adjusted r squared, we don't need to because we have the same number of variables here. Well, looks like my r squared is actually a little bit higher from that level model. Right? So that would be a good indicator. I should be using the the linear model to capture that relationship as opposed to the linear log model. Once again, I could also compare the test statistic on the nonlinear term to the test statistic from just the linear term. Which one is larger? The linear term, which would suggest it has higher statistical significance, right? Smaller p-value, we can reject at higher levels. So here I've got one. It's not always that it's going to be a nonlinear relationship. And even if it looks like there is, right? We looked like with that square term, it looked like it is a nonlinear relationship. It may not be a nonlinear relationship that's modeled as percent changes or through that natural log function. Okay. So up to this point, we have evidence that what's the best model? Well, here between the level log model and the level, the linear log model and the linear, I chose the linear. We go all the way back up here. What was I choosing? The linear model or the squared model. So here my r squared adjusted was 0.01017, here 0.0018. So of these three models, the one that best captures the relationship between happiness and hours worked would be this polynomial model where we included a square term. And if we wanted to, we could kind of look at maybe it's cubic, right? Include a cube term and then kind of, but for now, that was our best one. Okay. All right. Any questions up to this point? I've got one more main thing that I want to cover here today, and then I might have some additional comments at the end. Okay. All right. So we're going to go back now. Let's forget about the squared model for a second, right? And let's just assume we're trying to determine whether or not we should be choosing between a linear or a linear log model. Okay. So I said we can compare the r squared. That is a good first glance. There is a more accurate test, or there is a better test that we can use, which is called the Davidson-McKinnon test, right? So I'll outline it. I think it'll make more sense when we see it actually used in Stata, or I'll kind of write out the regressions. But I'll have two models, linear log. I'll run both regressions. Once I have those coefficients, I can then make predictions for what those y values should be. So for every observation from model one, I'm gonna store what the predicted Y value should be. I'm then gonna use those predictions, and in my second model, the linear log model, I'm gonna include the predictions from the linear model. I'm then gonna do the same thing. I'm gonna make predictions from my second model, the linear log model, and then put those predictions in my first model. Now I'm gonna look at the statistical significance of the coefficient on those predictions to tell me which model looks like it's better. I think this will make a little more sense when we kind of dive into this in a second. So I'll show you how we do it in Stata. I'm gonna write it out first, and I think it'll help. So let's say I've got model one is my linear model. So it's gonna look something like this, right? So this was my kind of linear model. If I run this regression and I obtain the coefficients on beta 0 and beta 1, for every observation, I can come up with predicted values for Y using the regression results that I got from model 1. I think we've talked about this before. If not, I'll remind you of what that command is, how you can very easily in Stata create the predicted Y value for every single observation. I'm then going to think about, okay, here I've got my second model. This was my linear log model. From this second model, I could come up with predicted Y values as well. Now, I'm not going to make you do these by hand. And it does get a little bit trickier with these log models to make predictions because I'm not just plugging in the value for X here. I would actually need to take those coefficients, and that slope coefficient would get multiplied by the natural log of X, right? So we have like an additional kind of mathematical step to do. We couldn't just plug in X, we have to take the natural log of X there. Now, once I have these two predictions, what I'm then going to do is take model one. I'm going to estimate model one, but I'm also going to include these predictions I made from model two as a separate variable. So what the thought experiment is like, okay, if I were to just use the linear term, holding constant that linear term, do the predictions that my nonlinear term make, do they have some statistical significance with that Y value? If they do, that's telling me that the nonlinear predictions are actually better than linear. I'm holding constant my predictions kind of from the linear model. If there's statistical significance on my predictions from the nonlinear model, that would suggest that it's better at explaining that relationship between whatever X variable I'm looking at and whatever Y variable. I would then do the exact same thing down here. I would run model two, but include the predicted values that I had for Y from model one. Now, if this is statistically significant, that's saying holding constant the predictions I was making with a nonlinear term, do the linear terms actually still have some statistical significance with Y? So if I can reject either of these coefficients, that's going to suggest that that model's predictions were actually better, right? So whatever model predictions I can reject the null for, that's going to be the model that we would say is better. So how do we get these predictions and how to do this in Stata? Yeah.
Can you just repeat that one more time?
So for this coefficient, if we can reject the null, right, we're saying that the predictions from our other model were statistically significant at predicting Y. So that must have meant that the linear term wasn't doing a good job because our second model's predictions still had some statistical significance with Y, right? So if I can reject the null for this second model's predictions, I'm saying really that model two was better at capturing that relationship. And if I can down here reject the reject the null hypothesis, I find that the predictions from model one are statistically significant. What that's saying is model one is better, right? So whichever model's predictions I can reject the null for, that's the one that is going to suggest that that's the better model. Yeah.
Have a situation here like earlier when both statistically significant.
So trying to remember the exactly what it's if I include additional control variables. If I include additional control variables, you could have that happen where you reject both. So kind of similar to what we would do before, you would just take whatever model you can reject at the highest level, right? I will always try to give you examples where that's not the case. And more often than not, it's not. But I'm trying to remember, I think theoretically, if I included additional controls in these models such that somehow they were correlated with the nonlinear coefficient in a different way than with the linear, I could end up with bias that exists in both of these that actually could, you don't care about all that, but like that, then there is some way where I could actually end up rejecting both because whatever variables I have in here, whatever is omitted, could be impacting the nonlinear coefficient different than the linear coefficient. But more often than not, we only end up rejecting one. Is that what you're asking? Yeah. So what does this look like in practice, right? So this might be something I asked you to do on that problem set. So let's say I come down here. Here's my linear model or model one. So I'm going to run this regression. It's just the linear term of hours worked. I'm then going to use this predict command. So what that predict command does is it creates a new variable. I've called it model one. I guess you could call it model one predictions if that made more sense to you. But these were the predictions that came from model one. And then the syntax XB, that just tells it, take the coefficients, multiply them by whatever the values are for the different variables X. Here we included what? Hours worked, children, and age. So it'll factor all of those into those predictions. Okay. So I'm going to run that. And what you'll see is I now have an additional variable, which is the predicted level of happiness for all of these different observations, right? From my first model. What I'm then going to do is run model two. This was our linear log model. I'm then going to make predictions for Y, call that model two. These are just my predicted values from that second regression, or, oops, I forgot my two here, model two. So now that I have those predictions, right, I'm going to go back and take my first model. So remember, my first model was just the linear relationship. It's going to be everything I had before, but now I'm going to include the predictions that I made from model two. So when I run this regression, I'm now interested in, well, what's the statistical significance of that coefficient associated with the predictions from model two? So in a weird way, it's like holding constant the predictions I would have been making from my linear term. Do the predictions from the nonlinear model have any statistically significant relationship with my Y variable of happiness? Well, here, what levels could I reject the null at? None of them. So this would suggest that model two's predictions are not good. I can't reject the null, but they have any statistically significant effect on the actual Y values for happiness. So that would suggest that model two is not good. Remember we said if we can reject that coefficient on the predictions from the other model, that means it's a better model. Here we failed to reject, that means model two wasn't as good. Didn't look like those nonlinear relationships were actually better. Now, I do the same thing. Doesn't look like the model two's predictions are any better. I'm not sure if I said that in the correct order. We can then run model two, where I was using the natural log of hours worked, but include the predictions from our linear model, model one. If I do this, well, now it's like holding constant the predictions I was getting using the nonlinear version of hours worked. Did the predictions from the linear model, right? That was model one. Do they have a statistically significant effect on those predicted Y values? Well, the 10 and 5% level, yes, they do. So this would suggest if we can reject the null, that the predictions had zero effect, we're rejecting that. We said that the predictions for model 1 actually had a statistically significant effect on our Y values, even holding constant, like the predictions from the nonlinear model. So that would suggest we can reject the null. Model 1 was better. What was model 1? That was our linear relationship. So remember when we were just going, if we go all the way back here, when we were comparing like the R squared and the test statistics, remember the R squared from our linear model and the adjusted R squared were a little bit higher. The statistical significance of that coefficient was a little bit higher. This is just another test of whether or not that linear model is better. All of them in this case suggest that the linear model was better. It can be the case that if you're just using the R squared and you're just using that coefficient statistical significance, and we're just looking at like the before we were doing this David-McKinnon test, it could be that those lead you to a different decision than using this Davidson-McKinnon test. It does a slightly better job at controlling for the difference in the variation that exists by taking the natural log. More often than not, all three of these things will lead you to the same model, right? But they're all just different tests of which model, or they would all be a test that suggests you should be using one model over the other. In this case, we had an example where all three of those things would suggest we should be using that linear model to estimate the relationship between hours worked and happiness. Okay. Any questions on, I know this is kind of difficult, like this idea of this Davidson-McKinnon test. I think at the end of the day, remembering when you're making these predictions, if you can reject the other model's predictions, if you can reject, that means the other model's predictions have a statistically significant effect, you're saying that that model is better. So in a weird way, like rejecting, it's kind of a good thing. It's a good thing for that model, right? It's a bad thing for model 2, right? But it's a good thing for the model that you're rejecting that coefficient on those predictions. Oh, sorry. I didn't switch this over here for it. That probably made no sense. Right? If I can reject model 1's predictions, that means I'm saying they have a statistically significant effect. I'm not rejecting them, I'm rejecting that they have no effect, right? So that's like saying, oh yeah, model 1 is better. So rejecting in a weird way is saying that model 1 is better, which is, means model 2 must be worse, right? Any questions over anything there? Let me see something again before we kind of get out of here for today. Okay. Well, I had one slide left in there, but we're kind of running out of time. I might revisit at the very beginning of class. I've got some additional examples using that happiness data set. I might go through them. We'll see. I'll think about it just to kind of see some more examples of this. We'll also talk about like the underlying assumption, the whole reason why we want to choose the right model. And then we'll very quickly probably move on to interaction terms. So we'll start interaction terms Thursday. It'll be all of next week. So at the end of next week, right, we're going to have the quiz and problem set due. I'll probably bring up the next problem set and quiz so you can kind of start working that early and get that out of the way. Okay. All right, make sure you get those corrections uploaded before the end of the day today. I'll start grading those as quick as I can. And we'll see you guys on Thursday.